Hello and welcome. In this video, we'll be diving into the world of exponentials. This is a fundamental topic in mathematics, with applications across many fields, from finance to physics. By the end of this session, you will be able to define exponents, apply the laws of exponents to simplify expressions, work with rational exponents, and solve basic exponential equations. Let's begin with a real-world problem to see why this topic is so important. Imagine you place a packet of peas into a freezer. The freezer's temperature is negative 10 degrees Celsius. The temperature of the peas, T, after t minutes, is given by the formula T of T equals negative 10 plus 32 times 2 to the power of negative 0.2T. This formula describes how the temperature of the peas changes over time. Notice the variable, T, is in the exponent. This is a classic example of an exponential decay model. Let's answer a few questions about this model. First, what was the temperature of the peas when they were first placed in the freezer? This means we need to find the temperature at time t equals 0. We substitute 0 for t in our formula. Any non-zero number raised to the power of 0 is 1. So 2 to the power of 0 is 1. This simplifies to negative 10 plus 32, which is 22. So the peas started at 22 degrees Celsius. Next, let's find the temperature after 10 minutes. Here, we substitute t equals 10 into the formula. The exponent becomes negative 0.2 times 10, which is negative 2. A negative exponent means we take the reciprocal, so 2 to the power of negative 2 is 1 over 2 squared, which is 1 over 4. 32 times 1 over 4 is 8. Negative 10 plus 8 is negative 2. After 10 minutes, the peas are at negative 2 degrees Celsius. Finally, let's consider the long-term behavior. Will the temperature ever reach the freezer's temperature of negative 10 degrees Celsius? Let's analyze the term 32 times 2 to the power of negative 0.2t. As time t gets larger and larger, the exponent negative 0.2t becomes a very large negative number. This means 2 to that power becomes a very small positive number, approaching 0. Therefore, the entire term 32 times 2 to the power of negative 0.2t approaches 0. This means the temperature T of T approaches negative 10 plus 0, which is negative 10. The temperature will get infinitely close to negative 10, but it will never actually reach it. This is a key characteristic of exponential decay. Now let's formalize what we've been using. We often deal with numbers that are repeatedly multiplied together. To write these expressions more efficiently, mathematicians use exponents. An exponent, also called a power or an index, tells us how many times to multiply a base number by itself. For example, instead of writing 3 times 3 times 3 times 3 times 3, we can write it as 3 to the power of 5. Here, 3 is the base and 5 is the exponent. It means we multiply the base, 3, by itself 5 times. In general, if n is a positive integer, a to the power of n is the product of n factors of a. The base is pri a, and the exponent is pri n. Let's look at how negative bases behave. This is a common area for mistakes. Consider negative 1. Negative 1 to the power of 1 is negative 1. Negative 1 squared is negative 1 times negative 1, which is positive 1. Negative 1 cubed is negative 1. And negative 1 to the power of 4 is positive 1. Do you see a pattern here? Let's try with a different base. Negative 2 to the power of 1 is negative 2. Negative 2 squared is positive 4. Negative 2 cubed is negative 8. And negative 2 to the power of 4 is positive 16. The pattern is clear. A negative base raised to an odd exponent will always result in a negative number. A negative base raised to an even exponent will always result in a positive number. This is because an even number of negative signs will cancel out to a positive. Now, let's be very careful with notation. What is the difference between negative 7 to the power of 4 and negative 7 to the power of 4 with the negative sign outside the parentheses? In the first case, negative 7 is the base, so we multiply negative 7 by itself 4 times. This gives us positive 2,401. In the second case, the base is 7, and the negative sign is applied after the exponentiation. So we calculate 7 to the power of 4, which is 2,401, and then we make it negative. The result is negative 2,401. The placement of the parentheses is crucial. Now that we understand the basics, let's explore the fundamental rules that govern how exponents behave. These are called the laws of exponents. These laws allow us to simplify complex expressions and are the foundation for solving exponential equations. First, the multiplication law. To multiply numbers with the same base, you keep the base and add the exponents. For example, 3 to the power of 5 times 3 to the power of 4 is 3 to the power of 5 plus 4, which is 3 to the power of 9. Second, the division law. To divide numbers with the same base, you keep the base and subtract the exponents. For example, 5 cubed divided by 5 to the power of 5 is 5 to the power of 3 minus 5, which is 5 to the power of negative 2. Third, the power of a power law. When raising a power to another power, you keep the base and multiply the exponents. For example, n to the power of 4, all raised to the power of 3, is n to the power of 4 times 3, which is n to the power of 12. Fourth, the power of a product law. The power of a product is the product of the powers. For example, the quantity a times b, all to the power of n, is equal to a to the power of n times b to the power of n. Fifth, the power of a quotient law. The power of a quotient is the quotient of the powers. For example, the quantity a divided by b, all to the power of n, is equal to a to the power of n divided by b to the power of n. Sixth, the zero exponent law. Any non-zero number raised to the power of 0 is 1. For example, 17 to the power of 0 is 1. This is a direct consequence of the division law. And finally, the negative exponent law. A negative exponent means you take the reciprocal of the base raised to the positive exponent. For example, a to the power of negative n is 1 over a to the power of n. This also means that 1 over a to the power of negative n is a to the power of n. For instance, 5 to the power of negative 2 is 1 over 5 squared, which is 1 over 25. Let's put these laws into practice with some more examples. Our goal is to write expressions as a single power of a given base. First, let's write 16 as a power of 2. We know that 16 is 2 times 2 times 2 times 2, which is 2 to the power of 4. Next, let's write 1 over 16 as a power of 2. We just found that 16 is 2 to the power of 4. So 1 over 16 is 1 over 2 to the power of 4. Using the negative exponent law, this is equal to 2 to the power of negative 4. Now let's write 1 as a power of 2. This is a direct application of the zero exponent law. Any non-zero number to the power of 0 is 1. So 1 is equal to 2 to the power of 0. Let's try a more complex expression. 4 times 2 to the power of n. First, we need to express 4 as a power of 2. 4 is 2 squared, so the expression becomes 2 squared times 2 to the power of n. Now, using the multiplication law, we add the exponents. The result is 2 to the power of 2 plus n. Finally, let's simplify 2 to the power of m divided by 8. We express 8 as a power of 2, which is 2 cubed. The expression is now 2 to the power of m divided by 2 cubed. Using the division law, we subtract the exponents. The simplified form is 2 to the power of m minus 3. Let's do one more example, involving negative bases and the power of a product law. Consider the expression negative 3 times a squared, all raised to the power of 4. Using the power of a product law, we can distribute the exponent 4 to each factor inside the parentheses. This gives us negative 3 to the power of 4 times a squared to the power of 4. Now we simplify each part. Negative 3 to the power of 4 is 81, because a negative base raised to an even exponent is positive. For the second part, a square to the power of 4, we use the power of a power law and multiply the exponents. 2 times 4 is 8, so we get a to the power of 8. The final simplified expression is 81a to the power of 8. Now we're going to extend our understanding of exponents to include fractions. These are called rational exponents. Rational exponents are exponents that can be written as a fraction, p over q. They are directly related to roots, like square roots and cube roots. Let's see why. Consider the expression a to the power of 1/2. If we multiply a to the power of 1/2 by itself, we use the multiplication law and add the exponents. 1/2 plus 1/2 is 1. So a to the power of 1/2 times a to the power of 1/2 equals a. Now think about square roots. We know that the square root of a times the square root of a also equals a. By comparing these two results, we can conclude that a to the power of 1/2 is the same as the square root of a. We can extend this idea. What about a to the power of 1/3? If we multiply a to the power of 1/3 by itself 3 times, we add the exponents. 1/3 plus 1/3 plus 1/3 equals 1. So a to the power of 1/3 cubed is a. Similarly, the cube root of a multiplied by itself 3 times also equals a. This leads us to conclude that a to the power of 1/3 is the same as the cube root of a. In general, for any positive integer n, a to the power of 1 over n is the n-th root of a. The denominator of the rational exponent tells you the index of the root. What if the numerator is not 1? For example, a to the power of m over n. We can rewrite a to the power of m over n as a to the power of m, all raised to the power of 1 over n. Using our new rule, this is the n-th root of a to the power of m. Alternatively, we could write it as a to the power of 1 over n, all raised to the power of m, which is the n-th root of a, all raised to the power of m. Both forms are equivalent. Let's work through an example. Write the cube root of 2 as a single power of 2. Using our rule, the cube root of 2 is 2 to the power of 1/3. The index of the root, 3, becomes the denominator of the exponent. Now, let's try a more complex one. The fifth root of 4. First, we need to express the base, 4, as a power of 2. 4 is 2 squared, so the expression becomes the fifth root of 2 squared. Now, we convert this to exponential form. The base is 2, the power is 2, and the root is 5. So the exponent is 2 over 5. The result is 2 to the power of 2/5. Now let's combine our knowledge of rational and negative exponents to simplify expressions without a calculator. This is a common type of problem in IB math. Let's evaluate 8 to the power of 4/3. The key is to look at the denominator of the exponent, which is 3. This tells us we need to find the cube root of the base, 8. We can rewrite 8 as 2 cubed, so the expression becomes 2 cubed, all raised to the power of 4/3. Now we use the power of a power law and multiply the exponents. 3 times 4/3 is 4, So we are left with 2 to the power of 4, which is 16. The value of 8 to the power of 4/3 is 16. Let's try another one, this time with a negative rational exponent. We need to evaluate 27 to the power of negative 2/3. First, let's deal with the negative exponent. This means we take the reciprocal. So 27 to the power of negative 2/3 is 1 over 27 to the power of positive 2/3. Now we focus on the denominator of the exponent 3. We need to find the cube root of 27. We can rewrite 27 as 3 cubed. The expression becomes 1 over 3 cubed, all raised to the power of 2/3. Again, we use the power of a power law and multiply the exponents. 3 times 2/3 is 2, so we have 1 over 3 squared, which is 1 over 9. The value of 27 to the power of negative 2/3 is 1/9. Let's do one more example to solidify this concept. Evaluate 16 to the power of negative 3/4. First, the negative exponent tells us to take the reciprocal, so we have 1 over 16 to the power of 3/4. The denominator of the exponent is 4, so we need the fourth root of 16. We can write 16 as 2 to the power of 4. The expression becomes 1 over 2 to the power of 4, all raised to the power of 3/4. Multiplying the exponents, 4 times 3/4 is 3. This leaves us with 1 over 2 cubed, which is 1 over 8. So 16 to the power of negative 3/4 is 1/8. Now we'll see how to apply the laws of exponents to algebraic expressions. We can use the usual expansion laws, like the distributive property and the binomial expansion formulas, to simplify expressions containing exponents. Let's start with an example that uses the distributive property. We need to expand and simplify x to the power of negative 1/2 times the quantity x to the power of 3/2 plus 2x to the power of 1/2 minus 3x to the power of negative 1/2. We distribute the term outside the parentheses to each term inside. This means we multiply x to the power of negative 1/2 by each of the 3 terms. Now we use the multiplication law of exponents. For the first term, we add the exponents. Negative 1/2 plus 3/2 is 1. For the second term, we add the exponents. Negative 1/2 plus 1/2 is 0. For the third term, we add the exponents. Negative 1/2 plus negative 1/2 is negative 1. This simplifies to x to the power of 1 plus 2 times x to the power of 0 minus 3 times x to the power of negative 1. Since x to the power of 0 is 1 and x to the power of negative 1 is 1 over x, the final simplified expression is x plus 2 minus 3 over x. Let's look at an example that uses the binomial expansion formula, specifically the square of a binomial. We need to expand and simplify the quantity 7 to the power of x plus 7 to the power of negative x, all squared. We can use the formula a plus b squared equals a squared plus 2ab plus b squared. Here, a is 7 to the power of x, and b is 7 to the power of negative x. Substituting these into the formula, we get 7 to the power of x squared plus 2 times 7 to the power of x times 7 to the power of negative x plus 7 to the power of negative x squared. Now we simplify each term. For the first and third terms, we use the power of a power law and multiply the exponents. For the middle term, we use the multiplication law and add the exponents. X plus negative x is 0. Since 7 to the power of 0 is 1, the middle term becomes 2. The final simplified expression is 7 to the power of 2x plus 2 plus 7 to the power of negative 2x. Just as we can expand expressions, we can also do the reverse, factorization. This involves finding common factors or recognizing special forms. Let's start with an example of finding a common factor. We need to factorize the expression 2 to the power of n plus 3 plus 2 to the power of n. First, we can use the multiplication law in reverse to split the first term. 2 to the power of n plus 3 is the same as 2 to the power of n times 2 cubed. Now we have 2 to the power of n times 8 plus 2 to the power of n. We can see that 2 to the power of n is a common factor in both terms. We factor it out, leaving us with 8 plus 1 inside the parentheses. This simplifies to 9 times 2 to the power of n. Another common technique is to recognize the difference of two squares. we need to factorize 4 to the power of x minus 9. We can rewrite 4 to the power of x as 2 squared to the power of x, which is 2 to the power of 2x, or 2 to the power of x, all squared. We can also write 9 as 3 squared. Now the expression is in the form of a squared minus b squared, where a is 2 to the power of x and b is 3. The difference of two squares factors into a plus b times a minus b. So our expression factors into 2 to the power of x plus 3 times 2 to the power of x minus 3. Sometimes we can recognize a quadratic form. Let's factorize 9 to the power of x plus 4 times 3 to the power of x plus 4. We can rewrite 9 to the power of x as 3 squared to the power of x, which is 3 to the power of x, all squared. Now if we let a equal 3 to the power of x, the expression becomes a squared plus 4a plus 4. This is a perfect square trinomial, which factors into a plus 2 squared. Substituting back, we get 3 to the power of x plus 2 squared. Finally, let's look at simplifying fractions with exponential terms. We need to simplify the fraction 3 to the power of n plus 6 to the power of n, all divided by 3 to the power of n. First, we can rewrite 6 to the power of n as 2 times 3 to the power of n, which is 2 to the power of n times 3 to the power of n. Now, the numerator is 3 to the power of n plus 2 to the power of n times 3 to the power of n. We can factor out the common term, 3 to the power of n. This gives us 3 to the power of n times the quantity 1 plus 2 to the power of n, all divided by 3 to the power of n. The 3 to the power of n in the numerator and denominator cancel out, leaving us with the simplified expression 1 plus 2 to the power of n. Now we arrive at one of the most important applications of exponents, solving exponential equations. An exponential equation is an equation where the unknown variable appears in the exponent. For example, 2 to the power of x equals 8 is an exponential equation. There are several methods to solve these, including graphing and using logarithms, which we'll cover in a later chapter. However, for many problems, we can use a simpler algebraic method. The key principle is this: if two exponential expressions with the same base are equal, then their exponents must also be equal. In other words, if a to the power of x equals a to the power of k, then x must equal k. Let's see this in action with our example, 2 to the power of x equals 8. Our goal is to rewrite both sides of the equation with the same base. The base on the left is 2. We can express 8 as a power of 2. We know that 8 is 2 cubed. So the equation becomes 2 to the power of x equals 2 cubed. Now that the bases are the same, we can equate the exponents. This gives us x equals 3. And that's our solution. Let's try a more complex example. Solve 9 to the power of x equals 27. The bases are 9 and 27. They are not the same, but they can both be expressed as powers of a common base, which is 3. We can write 9 as 3 squared and 27 as 3 cubed. Substituting these into the equation, we get 3 squared, all to the power of x, equals 3 cubed. Using the power of a power law, the left side becomes 3 to the power of 2x. Now the bases are the same, so we can equate the exponents. 2x equals 3. Dividing by 2, we find that x equals 3 halves. Let's do one more example that involves fractions and negative exponents. Solve 4 to the power of x equals 1 over 32. Again, we need a common base. Both 4 and 32 can be expressed as powers of 2. 4 is 2 squared, and 32 is 2 to the power of 5. So the equation becomes 2 squared, all to the power of x, equals 1 over 2 to the power of 5. The left side is 2 to the power of 2x. The right side, using the negative exponent law, is 2 to the power of negative 5. Now that the bases are the same, we equate the exponents. 2x equals negative 5. Dividing by 2, we get x equals negative 5 halves. This method is very powerful for solving these types of equations. Let's recap what we've learned today. We started by defining exponents as a shorthand for repeated multiplication, with a base and an exponent. We then explored the 7 fundamental laws of exponents, which are essential tools for simplifying expressions. These laws cover multiplication, division, powers of powers, products, and quotients, as well as the special cases of zero and negative exponents. We extended this to rational exponents, showing that a to the power of m over n is equivalent to the n-th root of a to the power of m. This connects exponents to roots. Finally, we applied these laws to algebraic expressions, using expansion and factorization techniques, and we learned how to solve basic exponential equations by finding a common base. You are now able to define exponents, apply the laws of exponents to simplify expressions, work with rational exponents, and solve basic exponential equations. To help you practice and master these skills, here are 5 questions with their answers. Take a moment to copy these down and work through them on your own. Remember, practice is key to becoming proficient. Once you've attempted the problems, you can check your answers. Here are the solutions. Compare your work to these answers. If you made a mistake, go back and review the relevant law or technique. Thank you for watching.